In this video, we're going to discuss the concepts of buoyancy and flotation and Archimedes principle. And of course, you remember Archimedes from the idea that the legend, the king asks Archimedes, hey, and is this crown that this jewel has made, or this merchant is selling me, is it made of gold, or is this like a fake thing coated with gold, right? And he had to come up with a system to test the gold without actually destroying the thing, because it would have been easier for him just to melt the crown and say, hey, it was gold, oh, but you lost the crown, right? So that's not a reasonable thing to do. Jewelers nowadays use electrochemical measurements or even like put acid or something like that to characterize gold. But at that time, of course, those things were not known. So Archimedes had to come up with something, and the story goes like he goes to take a bath, and then he observes what happens with the water, and then he says, oh, Eureka, and then he just runs away naked because he's very excited with the idea, right? That's the kind of the legend. So this is Archimedes' principle. So the idea here is, let's start with experimental observation. All the questions we're discussing today, or the questions of flotation and buoyancy, pull down to answer the same family, let's say, of phenomena, right? So we can say, for instance, why when I take a piece of iron and I drop it in water, it just falls, but if that iron, the same mass, now it's just making the shape of a boat, iron or steel or whatever, that thing doesn't sink. Or why I can take a beach ball and bury it in sand, but if I try to bury it in water, the thing just goes to the surface. Right? So these are kind of the questions that we're trying to answer. Or why do astronauts train underwater? If you've seen the videos, they train sometimes underwater. Why are they doing that? What's the idea in here, right? So the first thing that we're going to observe is that experimentally, if I have a block of a solid and I put it on top of a beaker filled with a certain fluid, right, and I just drop the object inside, what I observe next is that once the object is inside, the volume or the liquid raises certain height. And I'm asking, how much is this height is such that the volume of here is actually the volume of the object. And why does it need to be the volume of the object? Because the fluid is incompressible, in this particular case of course, and what we're observing is that whatever volume this object occupies inside, the liquid needs to make room for it. So it just distributes on the top just to make room for that. So that is the volume of the object. And importantly, of course, that mass, we will figure out how much is that mass, etc. Second idea we're going to discuss in here is just to remember what happens when I have an object submerged. Right? So let's say there's a beaker or container in here with a liquid, and then there's this object in here. Right? And then I'm saying, okay, what are the forces? I'm interested in the balance of forces on this object, right? And I'm analyzing the balance of forces. Let's see what forces are acting in here and what forces are acting on the other layer. Why? Because the force acting in here is going to be the same force as that one. The object, let's say, is not moving, and the forces and so forth, right? So let's analyze the force on that area A. First of all, the force that the area is experiencing is the result of the weight of the column in there. And we already have introduced hydrostatic pressure, so we immediately can say that if that's the layer A, and we can call that the height, this is height B, right? That's for area B, and the object has the same area, and there's no need to complicate it, right? That's B, and that's going to be A. So what we're observing is that the pressure at that point, the pressure at point A is going to be the rho of the fluid times gravitational acceleration times height of A. And the point B is going to experience similarly a density times G times HB. Now, we know that pressure is equal to force divided by an area. And so that means that the pressure times an area, it's equal to the force. So if I take now the object and I make a free body diagram, what I'm going to be observing is that there is a force pushing down, which is the force A, and there's a force pushing up, which is a force B. And I can make a free body diagram taking the box just to experience a force B and experiencing a force A. And actually, we shouldn't call this B and A. Let's call this 2 and 1. So that's going to be 1, and then let's call this 2. I mean, we can call it whatever we like, but you're going to see why in a second. So then what we're going to observe is that this is the force 2 and this is the force 1. Now, if you're confused, this is obvious why this thing is pushing down is because of all this column. But you say, hey, but what about here? You will only have that column, maybe the weight of the object itself, right? But that's not acting on that face. What's acting on the face is the volume, is the force of the fluid. And here's the thing: any point in the fluid which is in the same height, by definition, is experiencing the same pressure. We established that already. So I can bring it here and it's to establish the same pressure. And the force that it receives in every direction is also the force it's exerting upwards, because it's action and reaction. So whatever force is receiving from here is going down, but the same force is down, it needs to go up, because the force goes in every direction in fluids. And so that force is actually going to be the same as the force of a column of fluid of that height. That's another way of seeing it. In any case, you're going to have a force 1 in here and a force 2 in here. And the force 2 is going to be the pressure 2 times the area, and that's going to be the pressure 1 times the area. And so if I want to make the balance of forces, what I'm going to observe is I have the force number 2 minus the force number 1. And the force number 2 is going to be the rho of the fluid, which anyway, this is equal to the rho of the fluid times G times times the area, right? Both have the same area, times, and then the distance h2, which is h2 minus h1. And here's the thing: how much is h2 minus h1? This is h1, this is h2. I'm subtracting h1 from h2. What I'm finding is the thickness of the box. So that is actually the thickness of the box, and now I have A times T. What is that? That's the volume of the box. That's the volume of the object. So what's the balance of forces telling me? Is that I have a net force which is equal to the density of the fluid, gravitational acceleration, and volume of the object. And so what is this net force that I find? That's the force that I call buoyancy, or F sub B, and that's why I wanted to change. Buoyancy is going to be the density of the fluid times gravitation times the volume of the object. Let's erase this in 1 second and see some consequences of this equation over here. So now we have the idea of buoyancy, which is the result of the object being submerged, right, and experiencing a net force which is a buoyant force. And so we have said that that force is actually equal to the density of the fluid times G times the volume of the object. But what is the density of the fluid times the volume of the object? We can observe that the volume of the object, according to the first observation, is going to be the same as the volume of the fluid displaced. Remember when we had the level, we introduced the object, the level raised. That's the volume displaced. So then I can have density of fluid, volume of the fluid displaced, times G. But what is this? This. That's the mass of the fluid displaced. So how much is this? That's the mass of the fluid displaced times G. But what is that? Well, that's actually the weight of the fluid displaced, right? So now I can go back and realize that if I have an object underwater, right, this object experiences a force upwards, which is buoyancy, and it also observes a force downwards, which is its weight. And so the balance of forces is going to say that there is a buoyancy force and there's going to be a weight force. But what is the buoyancy force? That's going to be the mass of the fluid times G. And what is the weight of the object? It's going to be the mass of the object times G. So what makes this sink or not? We're going to have 3 scenarios, basically, for a fluid at a given distance or at a given depth, right? What we're going to observe anyways is that we're going to have the following scenario. We can just write G times mass of the fluid displaced minus mass of the object, right? That's going to be the balance. So what do we observe in this case in here when I have the balance of forces? There's 3 scenarios. So in the first case, what happens if the mass of the fluid displaced, in other words, if the mass of the object is larger than the mass of the fluid displaced, then what happens is that the weight of the object is larger than the buoyancy, and so this thing sinks, because it's going to have a net negative acceleration, and so that's going to be the sum of forces right? It's going to have a net negative acceleration, and so it's going to be kept going down and down and down. The second thing is what's going to happen when the mass of the fluid displaced is larger than the mass of the object. And then in this case, we're going to have that the buoyancy force is larger than the weight, and so the thing is going to float. And there's a third case, which we can introduce here, of course, which is what's the case when the mass of the fluid is the same as the mass of the object. And in this case, you're going to have an equilibrium, and so the object is not going to move. So it's going to retain whatever height it's in there, right? So this is, for instance, the case of the fishes. They have their swimming bladder, so they can increase or decrease to play with their densities, and so they can go deeper or lower. You can just also do something similar, but you're actually diving in, right? So this will be like the case of the fish. So we can put a fish in a fish tank, right? And the fish, let's make the fish a little bit larger. So the fish, and so the fish here has a inflated thing, and when you go down here, the fish has a closed bladder, sure too. Anyway, that's basically the idea. The same thing with the submarine. You have to adjust the height by basically playing with how much fluid you displace with the object. But this is the idea. Before we go ahead, why does this thing sink? That's something that we should mention is, what is the buoyant force of an object here or an object here? Remember, buoyancy is the difference between the pressure in top and bottom layer, and that only depends on the volume of the object. So if I go here, do I have a different density? No. If I go here, do I have a different gravitational acceleration? No. And I have a different object? No. So buoyancy is the same. Buoyancy does not depend on the depth. Again, assuming that the density is constant, which of course, if you go too deep, at that point probably you cannot hold that approximation anymore. But let's say for a reasonable depth, that's going to hold well. So buoyancy does not depend, again, buoyancy does not depend on the depth. Pressure depends on the depth, but because we're actually resulting, the buoyancy is the result of the difference in pressure because the object is extended, that only depends on how different or how tall, let's say, how much is the volume rather of that object. That's what is actually determining the buoyancy. So it doesn't matter how deep you are, because of course, if this is the pressure, let's say this is lower than the pressure here, but the pressure here even is larger, but that's also going to be the difference, the ratio of those are going to be the same. So I'd say 1 arrow up, and here I have 3 arrows down, but this is 1 arrow up. It still is the same. So that's the idea here of buoyancy. Buoyancy doesn't depend on height. So once you have submerged the liquid, the object, which means completely covered by liquid, that's submerged. What we observe is that if the weight of the fluid displaced is less than the buoyancy, the weight of the object is less than the fluid displaced, the object is going to sink. Whereas if I'm in a situation where the object has a larger fluid displaced, which is than the weight, right? In that case, I'm going to have a net positive force going up, so it's going to accelerate, it's going to go up. And how much is going to go up? That's what we're going to see next. We're going to see that the object starts to get out of the fluid. As it gets out of the fluid, it starts to displace less and less and less fluid. So this mass of fluid reduces all the way until you find an equilibrium. And so the object stays wherever it is, and that's immersed. So let's see with a little bit more detail. Now the last thing that we were discussing is what happens when the mass of the fluid displaced is actually larger than the weight of the object. That's what's producing a net force of buoyant force. Let's say that the object is submerged, and so I have a large buoyant force for a much less weight of the object. What's going to happen, of course, is that the object is going to be, and of course you imagine that I take the object, I submerge with my hand, and I remove my hand. And at a point I remove that external force, I break the equilibrium again. I'm removing the table when we were discussing the other day, so I remove that table, so I break the equilibrium because I remove one of the forces involved in the equilibrium situation. Now I have a net force pointing up, so the object is going to keep going up. But once it reaches the surface, we're going to observe that the object is going to start leaving that. And there's going to be a situation where the object stops just leaving the liquid, right? Let's say that's going to be like that. I'll make it a little like this, so it's more obvious, right? So a portion of it is submerged and a portion is not. So what happens, and what do we observe if we take an object and, right? We take the object now, and we just partially introduce it into the liquid. Well, what happens is that the new level of the liquid is going to be equal to the volume of the object submerged. Now that volume is not the entire object, it's just the object submerged. So then what we're going to observe is that the new balance of forces, right? We have the volume of the object submerged. That's going to be volume, of the object, that's the volume of the object submerged. So that's going to be V submerged, right? So what I'm going to observe is that I have two forces. One is buoyant force, but buoyant force is just due to the volume displaced. And now I'm not displacing the volume according to the entire volume of the object, but I'm just for the part submerged underwater. So the buoyancy force is, of course, going to be the density of the fluid, g, and now is at the time of the object submerged. Whereas the weight, however, is still going to be the same, which is going to be the density of the object, right? Or if you want directly, let's write this and then explicitly say that. That's going to be the mass of the object times g. But the mass of the object, of course, is going to be the density of the object times the volume of the object. And so I can write the volume density of the object, g, volume of the object. And now we're going to have a scenario where I'm going to have a pointing up force, which is the buoyancy force, minus, right, the net force is going to be the buoyant force, minus the force due to the weight. The buoyant force depends on how much is submerged, and this one is going to depend on the mass, and this is going to be the density of the object times g times the volume of the object. And if I'm in equilibrium, how much is the net force? 0. So then what I observe is that I have that the density of the fluid g times volume submerged is going to be the density of the object g volume of the object. And then I can cancel the g's, and what I'm going to find is that the density ratio, that the ratio of the volume submerged to the volume of the object, what percentage of the object is submerged over the total volume of the object, is going to be equal to the density of the object divided by the density of the fluid. So, if I want to have an object that is floating more, I need to have a ratio of submerged to object smaller, right? So obviously, V submerged over V object, in the case where I have this versus when I have, right? Versus when I have this, there is more submerged here in the air, the denominator is larger, so this ratio is going to be larger in here than here. And this is floating more. This one. So if I actually want to make things to float, I need to have a small ratio of volume submerged to the volume of the object, right? So let's say have a 10% here is smaller than 90% here. So that's the ratio we're talking about, is how much of the volume is submerged versus the total size of the object. And I observe the larger the ratio is, the more it's sinking in, to the point wherever all the object is fully submerged, and at that point buoyancy force maxes out because volume submerged is the same as the volume object, and then we have the situation we were discussing before. If it goes all the way in, it will go all the way to the bottom, because once the buoyancy force has max, which is whenever the volume submerged is the same as the volume of the object, it's going to be the same regardless of the depth. And if at that point in the surface, when everything is covered, the weight is larger than that buoyant force, it's going to be always larger, and it's going to keep going sinking until it reaches the bottom of the whatever that water or that liquid is. Okay, that container. Okay, so in here I say I want to have this number to be small. So how do I achieve that? Through two ways. How do I make things float? Two ways. First one, of course, have volumes which have high density, fluids that have high density. If this number is large, of course, this is going to be a large number, so the numerator being large means that this number is going to be smaller. If this is larger, this is smaller, because this is a division, right? This is larger, this is smaller, and therefore this is smaller, therefore we're in this situation. So I can have very dense fluids. So you float better in very dense fluids. Classical example, Dead Sea in Palestine, where you can see people floating, actually, right? Why do you see that? Well, because the salt of the water is increasing the density of the water to the point where this thing is saturated, I believe, and so at that point you have a very high density, so less and less of your body actually sinks in, right? Because your body has a density very close to water, so once you put a density of a fluid which is much higher, the higher the density, the more that you float. And you could think about liquids like, oh, would you sink in mercury, for instance, which is 17,000 times, right, that of water, right? So you have a much larger density. But of course, if you're designing a boat, you cannot change that. That's given by the medium in which you're traveling, right? If it's and this is an important thing, if you're traveling if it's a boat designed to be for a river or a boat designed to be on the sea, it's going to be different, not simply just from the point of view of the salt corroding the materials, but also from the design and structure, because in salty water is going to be density is going to be higher than in fresh water, and so the boats have a different ratio to actually float in one or another. They're designed to work better in one typically than another, right? So that I cannot change, that's the medium. How else can I change it? I need to make this what? Larger. Excuse me, I want to make this smaller. I want to make my density smaller, right? So the other option is just to make the density of the object smaller. But what is the density of the object? Well, the density of the object is the mass of the object divided by the volume of the object. If I'm designing a boat and I use, let's say, a ton of steel, how do I make my ton is fixed? So how do I make this larger? I keep the mass obviously lighter, so the lighter the better, but I increase the volume. So if I need to decrease the rho, I need to increase the volume of the object. And how do I achieve that? I take the same amount of material, but now I expand the volume. And so instead of having let's make it in here, instead of having, and with this we can finish this introduction, instead of having, let's say, a chunk of steel that sinks, now I'm going to make my steel like this. And so the steel it's like this, right? Now it's a boat. Let's make it down. That's going to be one scenario versus the scenario. Instead of having a ball of steel, now I can take the steel and make it like this. And so when the thing gets submerged, effective density of this is going to be the density of the metal plus the density of air, because it's hollow inside. Because it's hollow inside, actually the mass of the thing, it doesn't increase with the air much, so I can increase the volume without increasing much of the air. So the density effectively of that boat is decreasing. So I increase that volume with the same amount of mass. I increase the volume with the same amount of mass. I decrease the density of the object. Because I decrease the density of the object, I make my object to float more. And that is precisely the reason why boats float. What happens if you hit an iceberg and the iceberg cracks your hull? Well, water starts to flow in, and that water density is 1,000 times more than the density of air. And so what happens? Well, obviously the density is increasing, that instead of decrease increases, and as the density increases, you float less, and less, you start to sink and eventually reach the point where all the water inside is enough not to produce enough buoyancy anymore to overcompensate the weight. So in this scenario where this is sinking, the weight actually is increasing. I would even think it's not necessary, but basically you're losing buoyancy. You're losing that ratio. The thing is going to sink. And the moment wherever all the water is in there, so as not to have any more buoyant force larger than the weight, the thing goes all the way to the bottom. So this is the physics for buoyancy and Archimedes' principle, and we can use it in some problems. Let's see some examples. Let's solve some problems on buoyancy and Archimedes' principle. So let's start with problem number 7 for discussions. So it says there's what fraction of a piece of iron will be submerged when it floats in mercury? The densities of iron and mercury are given, and that's going to be 7,100, and this is 13,600 kilograms per cubic meter. Okay, and so we'd say what is the fraction of the piece of iron that will be submerged, right? So let's assume that we have some piece of iron of this shape, and it's floating on mercury, right? There's a beaker or something with mercury, and we want to know, hey, what's about this? What is the submerged volume of iron over the total volume of the object, right? So we're looking for the ratio of the submerged divided by the total volume of the object. Now from the question we see directly that this object is floating, and so we can assume it's in equilibrium. And even if we didn't study anything, we should be able to say, okay, the object always has a force acting on it. We can make a free body diagram for the object, and always has a force acting on it, which is of course the force of the weight. Any object on Earth has that force acting on it, right? And it's pulling down towards the center of the Earth. But this object is not moving down. So because we know there is a force, there needs to be another force such that the object is indeed in equilibrium. That is, that the entire force is equal to 0. What's that force? We just have seen it. That's the buoyant force. And now because the object is in equilibrium, what we know is when we just put the buoyant force minus the weight force, that's going to be mass times the acceleration vertically, where we can just take this to be vertically, right? Vertically. And so we can say that this is not accelerating downwards, it's in equilibrium, so that's equal to 0, which means that the buoyant force needs to be equal to the weight force. And once we have that, we can remember what is the definition of the buoyant force and what is the definition of weight. Of course, weight is going to be, let's write it down here, the buoyant force equals to the weight. And so we can, we can start by the weight. Let's just make some clarification in here. Remember, the weight, of course, is mg, but now we can write instead of mg, which will be the mass of the block of iron, we can write that this is the block of iron density times the volume of the object, the entire thing, because this is the entire thing that want to create the weight, and then it's going to be times g, right? This is the equivalent of the mass, right? So we can write a thing over here. We're going to have density of iron, volume of the object, times gravity. And what about the buoyant force? Well, the buoyant force is going to be also proportional to g, as we know, and that's going to be the mass of the fluid displaced. So how much is the mass of the fluid displaced? It's going to be, we could write it here, so the buoyant force is just the mass, is just the mass of the fluid displaced times g. But how much is that mass? That mass, of course, is going to be the density of the fluid times the volume of the fluid displaced. But the volume of the fluid displaced is, of course, the volume of the object submerged. So that, of course, is the density of the fluid. In this case, fluid is mercury, so we can just directly write Hg for mercury, and that's going to be the volume submerged times g. And so we can write that over here, and so we're going to have, so that's the mass of the fluid displaced. So that's going to be the density of mercury times the volume of the object submerged, times g. And so we can solve for this and say, hey, what is the ratio? Well, the ratio is the volume submerged divided by the total object volume, and that's just simply the g's and g's cancel. And so we come here divided, and this goes there divided, and that's just the density of iron divided by the density of mercury. And how much is that? Well, that's 7,800 divided by 10 to the 3 if you want, and then 13.6 10 to the 3, which is 0.57, or if we multiply times 100, the ratio is 0.57. We can just say this is 57%. So how much of the iron is going to be sunk? It's going to be 57% of the total volume of the object. Important thing here is this object, of course, is a solid and compact object, right? So the entire density is the density of the atoms of the iron containing there. If I want to make the object to flotate more, we have over here the density of iron. In reality, it's not the density of the iron, it's the density of the object. And so this is actually the density of the object, right? That's the density of the object. And this is the density of the fluid, right? This is the density of the fluid, and this is the density of the object. When the object is compact and it's just made out of one material, the density of the object is directly the density of the material. But if you have a composite, you have to find the equivalent, effective, if you wish, density of that object. And there's two ways of doing that. Of course, if you make a composition, so maybe you have iron and maybe you put some floating material, maybe some styrofoam or some sort of foam that has very low density. And another way is just to arrange this in a different manner. So, of course, in this case, this is floating anyways because mercury is very dense. It's highly dense, right? Mercury is a metal. It's a very interesting case because it's a metal that's actually in liquid state in room temperature. Most of the metals are actually solid, but mercury is in liquid state. It's still a metal. So one of the things that we could do, of course, is just to say that this was the thing. If in this case we had found that indeed the iron sinks, you can increase the density by just making this, maybe. Right, this is sort of this will be the iron, but now we make it out of air. And now the volume of the iron actually is, because water doesn't go inside there, right? Water, unless there's of course a leak in the boat, right? The water doesn't go in there. In reality, now the volume is going to be this, right? But now if you observe, the volume submerged contains the material of iron, but it also contains air, and air density is 7,800, let's say, times less than that of iron. So I'm going to be mixing this. If actually the volume of the air to the volume of that is 50-50, the effective density might be reduced to 50%, and so I'm going to have more flotation. In fact, that's how it works. So if you have a boat, and you're going to make it float, the iron sinks if it's compact, but you can increase its volume such that the density of the object, not the density of the material, in this case because we were assuming it's a solid and compact block, but the density of the object drops, and that's exactly how the boats manage to float, right? So it's a matter of how do we craft the shape such that the volume submerged eventually, right? We submerge more and more of the volume with less and less of the material actually being submerged and more of air, or let's say not, or something less dense than water and being submerged. So that's the idea anyways. In here, we can calculate how much, and actually we didn't depend on the shape or anything like that. We're just assuming the entire object being solid, and now we can figure it out. 57% of the object is going to be submerged. So problem number 8 on discussion presents us with a situation. It's a sort of realistic situation because we have observed this sometimes in the news as well. There's unfortunately a shipwreck and the ship sinks, not necessarily near the coast, let's say in profound waters, in deep water, so the sink actually sinks. And you say, can we recover that shipwreck? Can we just bring it up and recover the materials, right? This is particularly important if it has environmental consequences, if the cargo, for instance, was oil or something toxic, right? So we're gonna see how this works, and this also applies to the situation when we're having, or we're playing in the beach, for instance, with a bucket of water, and we're just pulling it up, and suddenly we go through a bucket or something. Even you can load the bucket with something heavy. You try to lift it through the water, and you're fine, but at some point you reach the surface of the water, and something changes. So this is exactly what we're discussing over here. It says there's a crane that lifts a 18,000 kilogram steel hull of a sunken ship out of the water. It says determine the tension in the crane's cable when the hull is fully submerged in water, and the tension when the hull is completely out of water. Okay, so let's just make this sort of thing. Let's imagine that there is a boat here with a crane somehow, you know, and just trying to bring from here the hull of another boat, right? So that's sort of the scenario in here, and this is just trying to bring it up, right? And we're obviously going to assume it just goes vertically because there's no interest in going diagonal. And so this is 18,000 kilograms, which we can directly write in scientific notation. And we want to know what's going to be the let's bring this thing closer. So let's say it goes something like this, right? So we now have a better scenario. So this boat is trying to lift this thing up. And so the question is, how much is the tension? What is that tension? What is that tension in here? But also what's the tension when the object goes above the surface of the water, right? So determine the tension in the crane's cable when the hull is fully submerged in the water. So first case is fully submerged. So let's write submerged. And here we distinguish between submerged and immersed. Immersed is just partially, submerged is fully. So that's sub below, right? So that is the distinction that we're making in here. And so we want to know what is the tension. So we can find the free body diagram. So now our boat becomes just simply a block, and we certainly know there is a force that's pulling up, which is the force of the crane, and that's of course the force of tension. Let's write it according to our old notation, the force of tension. Is there any other force acting on this? Of course there is. There's another one, which is what? That's the weight of the boat. Any boat has, that's a W, weight. Any object on Earth has weight. And what else do we have? Do we have any other forces in here? In fact, we do. What's that force? That's buoyancy. Every object that is submerged experiences buoyancy. And buoyancy is going to be acting also up because it's trying to oppose that. So we're going to have buoyancy. And now we can assume that the object has no acceleration. Let's say it's moving with constant velocity. So we can act and say that we are able to say that the net force is mass times acceleration. Let's assume this is not accelerating, so it's just moving with constant velocity, and which is usually the most efficient way of doing anything. So then the force is going to be equal to 0. So if I make the diagram of forces here, what I'm going to find is I have buoyant force plus tension minus weight equal to 0. And now I can figure out what are every one of these ones. So what's the buoyancy? Well, again, as before, buoyancy, it's equal to the density of the fluid, so as the density of the fluid, times the volume of the object submerged, which in this case, because it's fully submerged, the entire object is submerged, so the entire weight, and that's times g, and the weight is mass of the object times g. Okay? So we have to assume that the boat is made out of steel. And so steel density is, how much? 7,800, like iron actually. So maybe it's actually iron, not steel, but anyway. And the water is going to be 1,000 as useful. Okay, very good. So now we're going to have that this is going to be the density of the object times the volume of the object. So the weight is going to be the density of steel times the volume of the object times g, right? And so now I can write everything, and I can just see density of the fluid, volume of the object times g, plus the tension minus the density of steel, volume of the object times g, and that's equal to 0, which means that the tension is going to be the density of steel minus the density of the fluid, volume of the object times g. So this is basically the idea, which is just basically the difference between the fluid displaced and the weight of the object. Okay? So now we can just say the volume of the object. How much is the volume of the object? We don't know that, but we know the mass and we know the density of the object. So then we can just say that the volume of the object, let's write it somewhere here, the volume of the object, of course, is going to be the mass of the object divided by the density of the object. So we can replace in there. Let's write it in here. So it's going to be the density of steel, density of the fluid times times the volume of the object, which is going to be the mass of the object divided by the density of steel times g. And so we can replace the numbers in here. If you plug all the numbers, you get about 1.5 10 to the 5 newtons, right? So what's the tension that the boat experiences? 10 to the 5, 1.5 10 to the 5 newtons. So if this string was not capable of sustaining the stress, it would break. And that's very important because you might be able to pull this strength, but what happens, and that's part B, and for that we can probably erase over here. And let's see what happens when the boat goes fully out of the water, right? So that's the question, part B, no? It says the tension when the hull is completely out of the water. Now from the free body diagram, once we're fully out of the water, is the tension still there? Yes. Is the weight still there? Yes. But is the buoyancy there? No. So now the new situation is going to have this free body diagram where the entire force is just purely based on the tension. And if I want to make now the balance of forces, now the force is going to be the force of the tension minus the force of the weight, and that's going to be mass in the acceleration, but this is not moving, so this is 0, which means that the force of the tension is necessarily the weight. How much is the force of tension? That's going to be the mass of the object times 10. And because this is 18 10 to the 4, so we're going to have, which finally just gives you, right, 10 to the 4th and one more for 1.8. So now what I observe over here is when the object is fully submerged, the force is 1.5 10 to the 5. When the object goes above the surface, we have 1.8 10 to the 5. Of course, this is not just an abrupt change. We are slowly reducing the buoyancy. So we can actually maybe make a diagram so we can see it. So when the object is fully, let's make this is the water. Sorry, let's say this is the water. So when the object is in here, we observe buoyancy and we observe tension, right? And we observe weight. So, and of course, the tension needs to be such that there is an equilibrium, so we could actually make it sort of like in proportional. Let's make this graphically a little bit more representative. So now we have the boat, right? And we have, let's say, this big is the weight. And so down here, to move it up, we have to have two, one, let's say, tension and one being buoyancy. They don't need to be the same value. In fact, they're not the same value. Value. Because the buoyancy is just 300, about 300 meters. But anyway, 0.3 10 to the 5. So as I go up, what's happening is that the buoyancy force, and we should probably, what's going to happen is the buoyancy force is going to start going down, the tension goes up, the weight is the same. And as I am about to go through the surface, now the buoyancy is very little and the tension is much larger. And what happens when I'm completely out? So I can see that the full tension needs to be the one for the weight, right? The weight is the same, so the arrow should be always the same, but that's just for the idea of buoyancy. What's happening with buoyancy? Buoyancy is the same all over the depth. As soon as I start going out, the buoyancy starts to drop, right? That's the buoyancy force. And it goes eventually to zero whenever the boat goes above the surface. There's no more buoyancy, there's no more fluid displaced, there's no more buoyancy. So that's important because although I may be able to pull the boat up here and even start to extract it, I'm going to be going from a string that needs to, or a chain or a cable that sustains 1.5 10 to the 5 or 0.15 megapascals to one that needs to sustain 0.18, meganewtons, to one that needs to sustain 1.8 10 to the 5 newtons. And so there's 0.3 10 to the 5 newtons difference, and that needs to be accounted for when you're building this boat, and of course the stability of the boat, right? And that's very important because I might observe if I take a string, I may be able to pull it up, and as the buoyancy starts to drop, tension needs to increase because tension needs to be able to compensate for more and more and more of the weight. Again, the balance of forces. And if at some point that force is too much, then overcoming the maximum tensile stress of the cable is going to snap, the thing is going to fall down. That's just important thing for application if you ever have to recover a boat that has sunk. But also it's explaining how when you're going down, you're applying a force which your hands will be the tension, and now you're applying a tension under the water, but as soon as you go above the water, you have to start putting more force. Why? Because now the entire weight is on your hands, literally, right? So now you have to go up with more force, compensating for the fact that the fluid is not anymore pushing up. So the fluid, you can imagine as your friend helping you, but as you go out of the water, your friend just disappears or vanishes, which is what we're seeing over here, which we'll observe over here. Problem number 10 says there is, because gasoline is less dense than water, drums containing gasoline will float in water. Suppose a 210 liter steel drum, so the volume of the object being 210 liters, and remember the 1 liter, it's 1 cubic decimeter, and the 1 cubic decimeter, it's 10 to the minus 3 cubic meters. So that's going to be 10 to the minus 3 cubic meters, or just directly 0.21 cubic meters. Now the gasoline density, they tell us, the gasoline density is 680, the density of water is 1000, density of steel is 7,800 kilograms per cubic meter. Right? So it's still being just iron, maybe with some carbon or other metals they add for the alloys. That's basically the same as if we take iron. So the question is, what total volume of steel can be used in making the drum if the gasoline-filled drum is to float in fresh water? This is fresh water, right? So the important thing here, when do we say when something is floating? Obviously it's in equilibrium, and the condition is, of course, that the buoyant force needs to be equal to the weight. Let's make it again. We make an object and we say, hey, the buoyant force is pushing up, the weight is pushing down, the total force needs to be 0, and that just means that the buoyancy minus weight needs to be 0, which basically means that the buoyancy needs to be the same as the weight, right? This is the condition of flotation. Now the weight of the object is going to be just the weight of the object. So we can start by identifying that the weight of the object is going to be the volume of the object times its mass. The volume is going to be 210. Well, actually, it's going to be the mass of the weight is going to be, let's do it this way. The weight of the thing is going to be the weight of the can. So that's going to be the mass of steel times G, and this being the can, right, or the mass of steel, actually there, and then the mass of the gasoline times G. And of course, the mass is density times volume, so that's going to be the density of steel times the volume of steel, and that's going to be plus, G, or plus mass of the gasoline times, so that's going to be the density of gasoline times the volume, and the volume is going to be the volume of the object in this case, right, because it's filled with gasoline, and then everything times G. Let's go now to buoyancy and observe something. What about buoyancy? Well, buoyancy is the mass of the fluid displaced times G. The mass of the fluid displaced is the volume of the fluid, the density of the fluid times, which is going to be water. So that's going to be water. The density of water times the volume submerged times G. Correct? And now, of course, the idea is how much is the volume submerged. So let's just make a small diagram in here and say, okay, if I have the object in here floating, completely floating, when would that be? Well, would that be, for instance, if everything in here has less density than water? Then it's not going to be sinking, right? Because any fluid is always going to be always larger than, so it's just going to be above. We have to assume that this just barely floats because it still sinks. Gasoline floats, so we can just, if it was pure gasoline, it would just form a layer, the same way that oil goes in water, right? If it's sinking, it's because of steel. And so when I make sure that, let's imagine that we're fabricating a tank that we want to be strong, so I don't just hit it and it leaks, or yeah, I don't know, something like that, or if you compress it, the thing explodes or something, right? I don't know. The idea here, well, I think gasoline would, but anyway, we want to be safe, right? So we want to make as robust as possible the tank of steel. So we're going to be adding steel, and as we add more and more steel, the tank, of course, is going to be sinking down, 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 down. So the idea actually that we're trying to make is what happens when this is the water, the object is fully submerged, but just barely there. So let's say there's an infinitesimal layer in there which is actually floating, right? So the thing doesn't sink. Because if we add a little bit more of steel, the thing will go just to the bottom, okay? So that's the scenario. So what that means is the volume submerged needs to be the total volume of the entire tank, right? So that means, what is the total volume submerged? It's going to be the volume submerged. It's going to be the same as the volume of the object plus the volume of the total volume submerged. Everything is submerged, so that's going to be the volume of, we should put here gasoline instead of object, sorry. Let's put here gasoline. Because the volume of the object is the internal volume of the object, but it's going to have a layer, right? So I'm saying something like this. So this is steel, and this is 210 or 21 cubic meters. So that thing I need to add it, right? So the total volume, which is the volume submerged, is going to be the actual volume of the object, which again, everything is submerged, just barely there. It's going to be, this is air, and this is water, right? That's the idea here. It's going to be the volume of the steel plus the volume of the gasoline. And that's the one that we actually have in here. So let's say that the volume of gasoline is 210 liters, okay? Okay, with that, we come here and we just realize that that's the density of water times volume steel plus volume of gas times G. And now we can make the balance. This needs to be equal to that. So weight needs to be equal to buoyancy, which means buoyancy is density of water volume steel plus density of water volume gas, and that's going to be density of steel volume steel plus density of gasoline, well, that was volume gasoline, density of gasoline volume gasoline times G. G's and G's cancel, and now we're going to just solve for this for volume steel. Let's bring it here. So we have volume still is going to be density of water minus density of steel. This is going to be negative, so we have to have it somewhere else. It's going to be non-negative, so it's going to be also negative. So here we're going to have the density, there it goes, the density of gasoline, and this goes there, minus density of water, and that's going to be times volume of the gasoline. So the volume of steel eventually is just simply the density of gasoline, density of water, divided by the density of water minus the density of steel, times the volume of gasoline. And that's going to be 680 minus 1,000, 320 divided by minus 320. So let's write minus 320 divided by water minus this is 6,800, negative as well, and everything multiplied times 0.21. So if we make those numbers, it's going to be 9.9 10 to the minus 3 cubic meters, and 10 to the minus 3 cubic meters, that just makes that the volume of steel, which is 9.9 10 to the minus 3 cubic meters, we can write it as 1 cubic meter is 10 to the 3 liters, so they're going to cancel and we're going to say 9.9 liters. So how much is the maximum volume of steel that we can have? 9.9 liters of steel. In that case, you could just make the idea. So the total volume is going to be about 220, right? 220 liters, which is going to be 210 liters of gasoline and about 10 liters of steel. If you actually calculate what would happen with a 220 total large steel, obviously empty, that would also float, and that obviously will float going up because you will lose the weight of the gasoline, which is again the idea of buoyancy. But anyway, the idea here just basically, we are playing with how we arrange stuff to bring the effective density of the entire object down. How we do that, because we don't have a solid steel, now we just have a hole of steel, right? And the container inside, we just put the gasoline. The gasoline is less dense, so the gasoline will naturally float. The same thing that we have with a boat. In the boat we have air, right? And obviously some payload, but air. And if we have enough of that air, so the volume is not fully filled, then the boat is going to be able to float, because the steel around, even if those is more dense than the water, because of the arrangement, the volume displaced is much larger than they actually would be if it was compact. And that's anyways the principle of flotation. So problem number 11 on discussions. So there's a child of 32 kilograms, and he's trying to build a raft with bottles of 1 liter. Let's say bottles of 1 liter, right? These are 1 liter and of volume, and he wants to build a raft out of them so that he can just probably go through the river, okay? Sort of a Mark Twain-esque story. So basically here, we're going to build a raft, and we're going to know, hey, how many of these do we need to use to actually build something that sustains the weight? So let's imagine that we're going to represent the entire thing by just simply saying this is all of the bottles tied together with duct tape. And the problem, by the way, says that to disregard duct tape and the bottle. So that's obviously non-realistic. But in a first approximation, you can do that. Then you can use what engineers say like a safety factor, which is whenever you find the factor of the minimum thing you need to use, maybe multiply times 2 or something like that to be extra safe, and then you will be safe, right? So that's just a sort of design rules. Anyway, the kid wants to stay here on the raft, and then there's the water in here. So what we can assume is that the bare minimum, of course, is that he's just, because he's more dense than water, and that would be kind of without air, but there's certainly the fit. We're going to assume that this is the scenario, so the water is here, the raft is in there. So the raft is just barely like before, but just barely below. Because if it keeps going down, it's going to sink, right? So, if he increases more bottles, obviously he's going to be, the more bottles, the higher up he goes. So we're going to have the bare minimum, right? So that's going to be like about the line of the water. So what is this scenario? Well, if I make the free body diagram of the raft, I'm going to observe the raft has the weight of the bottles and everything, but we disregard that, and then the weight of the child, which is going to be due to the child, right? And then there's going to be a force pushing up, and that's the force of buoyancy. So then if I make the balance of forces, then let's make it maybe here. The balance of forces is going to say that the buoyancy minus the weight needs to be equal to 0, and that just simply means that the buoyancy needs to be the weight. Now let's write those things in here. Let's first observe what's the weight of this. Well, that's the weight of the child times gravity. And what about the buoyant force? Well, we can take a single bottle, and let's make it in here, for instance. So let's take one bottle and make the free body diagram for this bottle. This bottle has what? Its own weight, and it has a buoyant force. But there is no buoyant force, weight, so all the bottle has is pure buoyant force, right? So that's gonna make it. What's the buoyant force for the bottle? Well, that's going to be what? The mass of the fluid displaced times gravity. How much fluid displaces? Well, displaces that of the volume of the bottle times the density of the water. So now I have the density, the volume of the bottle is going to be 1 liter. The density of the water, the volume of the bottle is 1 liter. The density of water is the fluid, right? And that gravity is gravity. So now we have the buoyancy. So what's the total buoyancy that this guy finds? It's going to be n times this single bottle. So it's going to be n times raw water volume of the object times g. And so now I have to make the balance of forces, which says that the buoyancy needs to be equal to W, and so we're going to have n being the number of bottles, right, that we need. And so we're going to find that n, density, volume of the object times g needs to be equal to mass of the child times g. G's and g's are going to cancel, and so we're going to find that n it's equal to the mass of the child divided by density of water, the volume of the object. And that's the same as the density of water is 1000 kilograms per cubic meter. The volume of the object is 1 liter, which again, 1 liter is 1 cubic decimeter, which is 10 to the minus 3 meters, cubic meters. And so I can just write everything here, and the mass of the child is 32. So I'm going to have 32 kilograms divided by 1000, which is 10 to the 3. This is 10 to the 3, right? This is 1000, which is the same as 10 to the 3 kilograms per cubic meter, right? Times the volume of the object, which is 10 to the minus 3. And if we make those numbers, we just find that the number of bottles that he needs is 32 bottles. Each one of the bottles, in other words, is going to be able to hold 1 kilogram. And so 32 of those are going to be what he needs to get all 32, all of his 32 kilograms. This is mathematically and explicitly, but you can just be much faster. It's saying what's the volume if you disregard actually the scotch tape and the mass of the bottle, right? So the kid might be, yeah, let's play it safe. Let's make 50 bottles, right? Or let's make 64, a safety factor of 2 or whatever, right? Obviously, it doesn't need to be that much, but it's a way just to be safe. And then he said, I can see that maybe he can bring a friend. So the idea here is how much volume does displace 1 liter, a bottle empty of 1 liter, if we disregard again the volume of the container itself, right? So just what is the volume in there? 1 liter. But 1 liter of water is 1 kilogram, because the definition of a mass of 1 kilogram. The reference tradition has been like 1 kilogram of mass is the same as the mass of 1 liter of water, because then it is 1000. So 1000 kilograms per meter, or 1000 grams per liter. So how many grams per liter? 1 liter of water is 1000 grams, which is 1 kilogram. So how much is the buoyant force when I submerge a bottle? Is 1 kilogram. And if I'm saying the bottle doesn't have any weight, it's just purely force going upwards, which is, for instance, the problem that you see when you have a beach ball and then you push it down. And so I'm saying that if I submerge a bottle of 1 liter, I'm going to have 1 kilogram of force pointing up. So if I have 32 kilograms of force to put down, because I'm 32 kilograms, I'm going to need 32 bottles, which is, of course, what we obtain. So this is just the idea. If instead of water was something else, this wouldn't work. So for instance, if this was, if the density was, for instance, in mercury, but of course the child should never be trying to navigate sea of mercury, then he would need less bottles. Why? Because the density of mercury is much higher. So the volume that you displace with 1 liter of the mass that you displace with 1 liter is much higher. It's actually 13 times more. No, I think it's 13.6 thousand. So, so the idea here again, we're displacing fluid. The idea of Archimedes principle is how much fluid are you displacing, the mass of the fluid that you displace. You displace with your volume, but you displace the mass of the liquid. That's why it's the density of the liquid, although this is your volume, right? And in the case of a bottle, disregarding again size, walls and scotch tape, blah, 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 each one of those is pushing up with 1 kilogram. So that's why the bottle itself is just going to be pretty much floating completely above the surface, just slightly inside. Why? Because it has some weight because of the plastic, but that's all. And the air is pure air. In the air is 1,000th of the density of water. So you can see why the bottle just floats around. That's why, right? If I submerge it, the tendency is going to go up only if I put the force of the weight. But I only need I have 1 kilogram per each one of those, so 32 bottles are required in this case.